2023. Fait que je vais, présenter, Heather rapidement, puis après ça, je vais lui laisser la parole. Fait qu'on a la chance d'avoir aujourd'hui Heather McGrath, qui est, chercheuse au Centre canadien, de cartographie et d'observation de la Terre. Elle est, à Ottawa, mais on a aussi une antenne à Sherbrooke ici. Fait que Heather, c'est une, scientifique, spécialiste des données géospatiales, donc à NRCan, et puis elle est aussi professeure adjointe, à l'Université du Nouveau-Brunswick. Puis ses recherches se focus essentiellement sur la géomatique et l'observation de la Terre, particulièrement sur la cartographie des inondations, et aussi sur comment l'utilisation de l'apprentissage profond peut aider, à améliorer et accroître la sensibilisation aux cartographies, des inondations et des zones inondables, et puis pour fournir, in fine de l'information aux décideurs, aux citoyens, pour améliorer la prise de décision, basée sur des preuves scientifiques. Et que je vais laisser la place à Heather qui va nous parler de tout ça, qui va présenter aussi, un peu les programmes de stage au gouvernement fédéral et puis des opportunités de stage, qu'elle a avec nous via le programme DOTS. Fait que, Heather, you can start, whenever you want.
Super, thanks. Thank you very much for the introduction, and thanks for the invitation to present this work.
You're welcome.
Hopefully you can see my slide deck now
Yeah,
shown.
that's perfect.
So today the plan was to talk to you a little bit about some recent research projects, some that use machine learning around flood susceptibility mapping and high resolution flood mapping, and then a project that we had about flood depths, and then a couple opportunities for student internships or supportive research through our RAP program. And so I'm sure many of you are aware that flooding is certainly an issue in Canada. There's been a lot of investment recently in a national flood hazard inundation mapping program, and we have quite a history of flooding. Recently, NRCan released the historical flood events data layer, which is just a point data set that is a record of all of the flood events that have happened that we could source. These are just point locations kind of at the centroid of a city where we've recorded or found record in publication or a newspaper where floods have happened. And on the right is our historic flood events that have been derived from satellite observations since about 2011. So we can see quite across the country, there is a fair amount of flooding. And in Canada, there's lots of different sources of flooding as well. The most common, or what we think of the most, is the kind of rainfall coupled with the snowmelt in the summer or in the spring, sorry. So we have that spring freshet. But we also have flooding due to ice jams where ice builds up on the river, kind of holds back water. And when the ice breaks up, we have kind of a strong release of fast flowing water down the river. The catastrophic outbursts that are more commonly found in the Western Canada, where lakes are dammed by glaciers or moraines, and they suddenly drain with tons of water, mud, and debris. Coastal storms, surges, tsunamis that bring big waves after earthquakes, cyclones and hurricanes. And then we have in our cities, we have urban stormwater runoff. So in cities that have built up, we have changed the kind of watershed flow patterns and implemented all of our infrastructure. And sometimes we have too much rainfall that overwhelms those systems, and we have the stormwater runoff and dam failure. So there are lots of different reasons why flooding can occur. Most of the research that I look at looks at inland flooding, mostly related to snowmelt and heavy rainfall, because some of the forcing factors for coastal and ice jams are a little bit different. Typically for flood hazard mapping, it's done through solving numerical equations which predict flood boundaries based on hydraulic and hydrologic modeling. However, there's been a really big growth in using AI and specifically machine learning algorithms in the recent years. So they've been shown to be really competent tools to identify areas that are susceptible or possibly prone to flooding. And so when we were looking at kind of creating a national flood susceptibility data set, we wanted to see kind of where are the gaps in the literature, where could we kind of create a contribution and how we could go about creating this national flood data set. So we started looking at the variables or the data sets that are used. And this is kind of a summary table grouped into kind of major categories of meteorological or your weather data, your hydrography, your geology and ecology, which affect the infiltration or the runoff rates, characteristics of the terrain, and kind of some of the urban built up as well. So we wanted to see kind of where there hasn't been a lot of input considered in these data sets. And so that led us to kind of our first research question, was assessing the importance of locally relevant meteorological variables. When they do flood hazard modeling using the hydraulic and hydrologic models, they use data sets that accurately describe the local hydrology, might include measurements of precipitation, temperature, snow water equivalent, water levels, discharge, groundwater. So lots of information about that local watershed to give them a really good idea of what that looks like and what the hydrology looks like. But typically, the machine learning models that are in the literature right now only consider average annual temperature or average annual precipitation. So it doesn't necessarily capture those small scale events that really lead to the flooding. So our objective was to then evaluate the impact of locally relevant meteorological data sets on flood susceptibility. So we started with kind of a exploration of the nationally available data sets that we had. So we started with elevation. Elevation is often kind of quoted to have about 90% of the importance in the model. So it's really quite relevant. It gives you indication of which direction the water will flow. And we have all these derivatives that we've created from the elevation data set to kind of help enrich the data and enrich the model. We wanted to know what the local hydrography looked like as well. So we have our water bodies and our flow lines. And from that, we created a Euclidean distance raster. So we created a raster that says, you know, how far away you are from a river and a lake, and created this continuous data set across Canada. We looked at where the wetlands were. There's a data set available for the minimum snow and ice, as well as a ground ice abundance, because in the north, we've got different conditions with permafrost. We looked at data sets that kind of impact or influence whether the water will run off the surface or infiltrate into the surface, and at what rate that might impact it. So these are the data sets that we looked at, looking at soil type, surficial geology, things like land cover and treed land. So these all kind of helped give indicators of, yeah, how that water, once it lands on the terrain, what it might do. And then finally, we looked at a number of data sets related to temperature. So we do have average annual precipitation and temperature, but we also wanted to capture some of those small scale events. So the number of days with rain that were greater than 10 millimeters, or the days with rain that are greater than 25 millimeters, to capture some of those short storms. Taking a look at the total snow, or areas that have a snow depth of greater than 50 centimeters. So we wanted to kind of, get a full picture, if we could, of the data sets that we had that were nationally available, and see how many of these are actually important in the machine learning model, and see how those kind of worked out. So we started with 5 primary study areas, A, B, C, D, and E, that are labeled there. And these are areas where we have record of floods that have occurred in the past. And so we set up an equal number of training points for our labeled points for wet, so areas that have been flooded in the past, and areas that have not experienced a flood. And to answer the question of whether the locally relevant climate variables are important, we started to create 3 tests. One where we just looked at the hydrology and the geomorphology. The second, we added that average annual precipitation and temperature. And in the last test, we added kind of that full suite of 8 different climate variables. We did all of our work for this in R, and for this part of the experiment, we used the vsurf library, which is the variable selection using random forest, and we were able to kind of run through put in all those 31 data sets and have the vSurf model kind of determine what it thinks are the most important variables out of that whole lot. And in the first test with just the hydrogeomorphological, we end up with 10 variables that are important here on the bottom right under predictive models, with our digital terrain model and our hydrographic network Euclidean distance being kind of the highest ranked. Those are considered the most important. When we ran the second test and we added in the precipitation and average annual temperature, those are actually replacing some existing variables. So they're up in here in our third and fourth position. And when we use this model, it actually decreases the number of explanatory or important variables. So we now actually only have 7 variables in this list, still keeping that digital terrain model and the hydrographic network as our kind of most important variables. And then we ran it a third time with all those additional climate variables. We again see the DTM and the NHN staying in their first and second ranked position. This is an example from the New Brunswick case study. And we're back up to 10 kind of exploratory variables, but of them, there's about 5 here that are all the climate variables. So we're seeing that as we're adding these climate variables, they're actually kind of outranking importance than some of the kind of traditionally used variables, which is really interesting to see. And once we kind of had an understanding of what the important variables were, we wanted to run a model to see actually how it performed. So we have 3 metrics that we measured. One is the accuracy, which is kind of like the total correct predictions over all of the pixels. We have the true skill, and then our F1 score, which is a measure of the precision and recall of the classifier. And then we've got our 5 sites here down on the left, each of the rows. And we don't see a huge improvement. We do see a marginal improvement between the HG to the HG8M. It's not hugely significant, but it's not making things worse. So that was interesting to see that it is actually making a marginal improvement. And then we wanted to kind of map that out and see what that looked like as we plotted it and comparing it against historic data. So here's an example of, again, that Fredericton study area with each of the 3 tests, the HG, the added precipitation and temperature, and the full speed of climate data. And we're able to look at kind of the distribution of the pixels in those histograms along the bottom to see kind of how it's measuring. So with just using the terrain and the hydrography and those soil, superficial geology, land cover, it's showing the mean value of the pixels within this flood extent is at 80. And when we add in those additional climate variables, it's increasing the mean up to 88.99, which is quite a jump. And it's showing that actually by adding these meteorological variables, it actually really is improving the quality of the model the outputs that we're getting. So we found that they have importance, and often these locally relevant climate data sets are more important than traditional data sets. Marginal improvement or minimal improvement in the validation metrics of the accuracy, the true skill, and then the evaluation of those prediction pixels with the historic flood event confirmed our hypothesis that if we include this locally relevant data, that will improve the resultant flood susceptibility map. So with that bit of information, our next step was to say, okay, we've got this really vast country. We're seeing that these locally relevant climate variables do make an importance or make an improvement. How can we kind of scale this out and create a Canada-wide flood susceptibility map? So we wanted to test if we should use a multi-regional model or a single regional model. So as an example, on the left here, we have these terrestrial ecozones of Canada. And so these are different like ecological growing zones. And so we wanted to see, can we use the training data that we have and create kind of models for each of those ecozones and then stitch those together to create a single susceptibility map? Or is there a way that we could create a national list of important variables put all of the training data into one model and create a flood susceptibility map. So again, we went through some testing of what the results look like. So we have for each of the sites, so BC across to New Brunswick, in the left, we have the locally important variables, giving our accuracy metrics of showing our accuracy, our kappa, sensitivity, specificity, and so on. And then in the right-hand side of the same column is when we use that kind of national aggregated list of important factors. So in BC, instead of using these 9 variables for the local, in the second column, we're seeing kind of this whole national list to see kind of what the impact is. And then we also ran a single model, putting everything together and estimated what those metrics look like as well. And so looking at all the numbers in the table, we found that there's like a slight improvement in most of the regions when we use a single set of national factors. So we're not necessarily decreasing the performance according to these metrics. And the other thing that we found is that when we tried to stitch the different regions together, like if we tried to stitch the boreal plains with the mixedwood plains, there was kind of differences at those borders. So the mosaicing process was a little bit challenging. And that was looking to introduce more errors than just a single national model. So we decided to kind of go forward with just this single model using this national list of data sets. And so we tested that out using several different machine learning models. Kind of before, we were just using random forest as kind of the primary kind of decider primary model. But we wanted to see kind of, once we applied this across the country, how does that scale with distance and variability with the input data sets? So as an example here, we've got the location of those historic floods and kind of the primary sites for our training data. And then we've got 4 different models shown here. We've got random forest, neural network, SVM, support vector machine, and this Mars model, to see kind of how those kind of scale with distance. And with the SVM radio, we can see that the model definitely had challenges up in the north with these kind of concentric circles that we're seeing. So there's definitely some issues as it's kind of translating distance from the area that it was trained in. And the neural network as well, we see kind of fairly good performance where it's flooded, but where there's limited data, we have just really, really low predictions. So the last thing we tested was an ensemble of models, putting those together to see if we could kind of minimize the bias of any of the one given models to create a national flood susceptibility data set. And then we also took a look at some of the kind of statistics of what those pixel values look like. So if we look at the regional approach using the parallel random forest, we look at the pixel values of just the points that we use for training, the pixels kind of around those training sites and kind of within that region, and then kind of all the pixel values across the country, and kind of looked at that at the regional approach using a national approach, and then using that final national ensemble. And we found that the national ensemble did perform the best when we looked at those pixel values compared to the historic location of events. And on the right-hand side, we see a map showing kind of some classes from low to high, so from green to kind of dark red, classed low to high risk or high susceptibility in a couple different locations. And in black is the location of historic flood events that were mapped by satellite to give us an indication of how the model performed and our classification ranges work. And so that seemed to go well. We're very happy with the results. And so we wanted to take a look to see if we could do mapping, multi-scale mapping under some climate change scenarios. So one of the goals of using this locally relevant climate data is, can we, kind of build on that and extrapolate to future scenarios? So last summer, we had a posting to help us work on this project, and Erin or Mingi Lee came and worked with me for the summer and tested this work in a discrete global grid system, looking at around southern New Brunswick. So there was 5 kind of large floods, or 4 large floods that she looked at from 2018 to 2019 that happened in the lower St. John River. And then we also have some future climate data from this PAVX platform. So we were able to have these same variables for locally relevant fall, spring precipitation, snow, temperature from 2040 all the way up to 2100. And so she ran a machine learning model. She looked at random forest and a few others as well, and was able to come up with some maps and some predictions of what that flood susceptibility looks like. And so this is comparing it against to the events that happened from 2018 to 2019, and at her 3 levels of resolution. Level 23 was about 30-ish meters. I think level 19 was about a kilometer or so per pixel. And then ideally, we want to have our true positive as large as possible and our true negative as large as possible, because those are our kind of correct predictions. And then we've got the false positives and false negatives that we wanted to minimize. And so she was able to kind of run through that and map those out. And then she went to the model and applied it to those future climate scenarios. On the top, we see it compared against the 2019 flood event. And so we have a 2040 to 2100 maps of flood susceptibility under 3 different future climate change scenarios, giving us an indication of what this model is predicting as the flood susceptibility. So we're obviously seeing an increase in flood susceptibility over time, and these events are looking larger than the 2019. And then on the bottom, we've just classified that into ranges of 20%, so 20 to 40, 40 to 60, and our highest there in orange, showing these are the highest susceptible pixels. So this was a really interesting work to take the kind of background information that we had started with and apply flood susceptibility to future climate change scenarios to see what the change in susceptibility might be. And if we turn a little bit, we also took a look at a kind of flood hazard mapping using machine learning to fill in the gaps. So worked with a master's student at the University of Ottawa and her professor Clement on this project for harmonizing and extending fragmented flood maps. So flood hazard mapping exists in Canada, and we have at the moment kind of a patchwork of these kind of regulatory maps that are created. They are mapped based on provincial and territorial responsibility, and they identify regions of interest, maybe the highest risk of flooding to a population, and these areas are mapped. But there's not necessarily continuous coverage because there's only maybe targeted areas that are of most importance. And so we wanted to see if we could take these kind of patchwork of maps and see if we could use machine learning to create a continuous map. So the research question was, how can we fill in the spatial gaps between these fragmented maps using machine learning? So we started looking here in the Ottawa-Gatineau region, and it was kind of interest for a couple reasons. Because the flood hazard mapping are provincial responsibilities, they may not use the exact parameters, the exact settings, and they might be set up to a different constraints and as they're modeled. So it was interesting to have both Ottawa and Quebec as or Ontario and Quebec as extends on either side of the Ottawa River. So we wanted to see how we could work. So we started with the first set, which was just a single training site, kind of centered on Ottawa and Gatineau. And then we extended it to these training sites 2 and 3 and incorporated those into the model as well. You'll see we didn't have the best performance with this. So this work is a little bit different than the first project. The first project was national. We are looking at about a 30 by 30 meter pixel resolution, and it covered a large area, different weather, different climate, different temperatures, and so on. But in this project, we're covering a pretty small area. So we looked at high resolution data sets. So we were using our high resolution LiDAR DEM product and created several derivatives of it in order to see, at this local scale, at this resolution, is there a difference in the important variables and how the modeling will work. And then we also included a couple data sets that weren't at 1 meter resolution, but we wanted to see if their importance would work. So we did resample those down from 30 meters for the land cover and the superficial geology. So our method was similar to previously. So we found the existing flood hazard maps, created training points from those. We tried with a single site of just 10,000 points, and then we have our multi-points, our multi-sites, where we have training points for each of the sites and combine those together. We went through testing to find the kind of conditioning or the important variables, and then split the data into 70-30 for training and testing. Again, we used vSurf in order to find the kind of optimal data sets to use for this project. And then we trained the random forest classifier to come up with a model, and then ran that on our testing subset to create this flood susceptibility map. And then for this one, instead of having just a range from 0 to 100 for flood susceptibility, we wanted to see how we could look at those pixels and recreate a polygon that represents the 100-year flood line. So we did a statistical evaluation of the pixels in those areas, and we came up with a mean 1 standard deviation and 2 standard deviation polygons based on thresholds. And so we'll show you what that looks like here. So on the top, this is just the model using just the kind of single study area around Gatineau and on Ottawa. And the model, while doing a good job within the extent of where it was created, when we go to the west, ultimately it didn't perform very well outside of the area that it was trained on. So the incorporation of these additional sites has really helped strengthen the model. So if you have data sets at along a river that you're able to kind of stitch together into a model in order to kind of recreate this 100-year floodplain, it did a much better performance by adding in these multi-training sites. And then we have the histogram here on the right, showing our mean standard deviation and 2 standard deviation that we used as thresholds for the pixels in order to identify the areas that were within that 100-year floodplain. And so the final result with the map classified into those kind of 3 thresholds, we have the permanent water here as blue, and then we've got our training sites as well as kind of these additional sites where we didn't use data in the model to get the results, but we were able to do a bit of a comparison because there is some data available. So if we kind of zoom into each of those sites, and in the black line with the hatch pattern, we're able to overlay some data from our National Flood Hazard Data Layer, which is a compilation of data supplied by the provinces and territories to give us an idea of what the flood extents look like. And so overall, the model has done a fairly good job. There's still room for improvement, but it was a great first effort to see kind of how we could use AI and those historic flood maps or those hazard maps in order to create a 100-year floodplain polygon in between existing data sets. So ultimately, our conclusion was it was a time and cost-effective solution to kind of harmonize and extend the flood hazard maps. And the process right now, in order to generate those, can be quite time intensive. And so this is a potential solution to help harmonize and extend those. And the last project I was going to talk about is some of our work on flood depths. So these are flood data products that can help aid emergency response, as well as be used for kind of potential estimating cost or economic impact after a flood. And for this work, I worked with a now PhD candidate, Seth Bryant, who's at the University in Potsdam, and a professor from UQAM. So within the Government of Canada, there's a response for ice breakup and flood events, and that's managed by the Government Operations Centre at Public Safety Canada and the Department of National Defence. Here at Natural Resources Canada, we have a group called the Emergency Geomatic Services, and they provide critical near real-time information to public safety and emergency responders during these breakup and major flood events. And this Emergency Geomatic Services, this EGS group, creates those flood extent maps and river state maps based on satellite information as events are unfolding. So we have an example here where they use satellite imagery. They use both synthetic aperture radar as well as optical imagery in order to create a picture of the event of the flood as it's happening. And they have several classes where they're able to specify whether it's permanent water, flooded vegetation, urban flooding. So this extent is really valuable for emergency responders in the field to know where the flood event is actually happening. But if we can add to that and give them information about water depth, that gives them kind of an extra level of information that could be used for supporting like road closures or things like that. So we worked on this and ended up publishing the work in the Natural Hazards Earth Science System journal last year. And creating flood depth maps isn't kind of novel, but there are several tools out there, but we found that there were several limitations when we were viewing the existing tools, and our work kind of tried to minimize some of those issues we identified. So some of the goals that we had for this work was to make the program automated. So we didn't really want to have a user or an expert user parameterizing or putting out information. So we tried to really minimize that in our work. We wanted to try to develop a method that didn't require both bathymetry and topography. We often don't have like the bathymetry of a river. And so we wanted to see how we could create a flood map without that and not overestimate by too much. Some tools have like kind of a flat shoreline kind of expectation, whereas in reality, often the river surface might be a little tilted. And then also the treatment of water depth at the boundary. Many of the tools that we looked at assumed at the boundary of the flood, all of the pixels would be kind of near zero or a zero water level, which is true in many cases, but you may have like curves or a bit of a slope. And so you might actually not have a zero water level at every location across that perimeter. And then finally, the assumption that the satellite-derived flood extent is correct. It's correct as it can be, and it's certainly, but we had some challenges of just that the resolution of the synthetic aperture radar isn't necessarily as high as the 1 meter DEM that we're working with. So we had to figure out how we could work with the resolution and the accuracy of the satellite-derived flood extent and the method that we are going to use to try to create a flood depth raster. So it's kind of a two-step process that we started with our approach. The first was to take the satellite-derived flood extents from EGS and merge that with our permanent water body polygons in order to be able to have a clear identification of what is permanent water and what area is flooded. And from that, we were able to generate points on valid edges of the floodplain extent. And from that, we used this hand submodel in order to sample what the hand values were at that perimeter. And a hand model is basically a depth normalized, height normalized DEM. So you start with a digital terrain model, and we use flow direction and flow accumulation in order to create this hand model where the pixel values, instead of being relative to a geoid or a mean sea level, the height values in this hand model are relative to its nearest drainage and based on flow direction and flow accumulation. So we have this hand model that we're using, and we're extracting values along the perimeter. And from that hand value, or that hand raster and all those points that we were able to calculate, we looked at the third quantile of the sampled hand values in order to create a threshold. And then we applied this max inundation filter in order to figure out, kind of based on this hydro-corrected hand surface, where we expected the inundation polygon extent to actually be. And in the second step, we then ran through this algorithm for generating a rolling hand grid and water surface level. So we had those sample hand values. We found like the max floor, or the max ceiling, and the minimum floor from that. We built some interpolated hand surface from there, masked out the regions that we did not need, ran through an interpolation of those internal values for the hand, and then ran a smooth low pass filter or our rolling hand grid over the data set as is shown in F. We then generated a set of hand inundation set, and from that we were able to get the water surface level from the hand depths, and ultimately ended up with a mosaic of our hand grid data set. In order to test how this process worked, we had two case studies, one in Montreal and one in Fredericton, New Brunswick. And we have our record results that we were able to generate, and we compared it against a tool called FWDeep that is available, and it has a QGIS plugin as well. And we compared it against some hydrodynamic models that were developed either by Montreal or in the province of New Brunswick. So those were our kind of baseline of what we were comparing our results against. And we have here an example. The top is A, this is our control. This is the hydro model that was run by the province. B is the result from the FWDeep software. And then the bottom result is our record result. And so we can see some challenges in the FWDeep, kind of in the middle of the floodplain here, some really low values that were in areas that weren't flooded. And then we also did kind of a wet-dry performance for those two study floods as well. So the first column is the FWDeep, the middle column is the record software, and the right is the control either from Montreal or the province. And A is our Quebec study area, and B is the New Brunswick study area. And so we can see we definitely made some improvements. We are not perfect. We still have some room for improvement. The model did better kind of in our New Brunswick study area, but we have definitely seen some improvement in performance from the FWDeep software. So that gives us some positive results that we're moving in the right direction. And so our results or our findings from that was that we're able to kind of create an efficient method to create a flood depth polygon that gives us kind of better results than what was available existing to date. It incorporates some error correction of the approximate inundation polygon and is structured around this hand submodel in order to create or facilitate these more realistic water surfaces. And so yeah, that's been some positive results that we've seen as well. And And now I will just talk a little bit about some research opportunities that we have at NRCan. So we have two ways that we support research and support students. One is through this research affiliate program. These are designed to give like master's and PhD students experience in applied research. We have a number of jobs posted, and they're jobs, but you're a full-time student, you work at the university, and the government essentially pays you a bursary through 3 installments to kind of support your research. We often suggest a topic or a theme for what your research thesis would be, and kind of co-supervise you along with your university or your academic supervisor on some work. The eligibility requirements are quite low. You just need to be a full-time student, required in a program that has research as part of your curriculum. So it needs to be a research or a thesis-based master's or PhD. So that is one option. And then the other we have is some internships. So these will just be like a couple months worth of work. And I have 2 projects that I'm kind of looking to fill right now. One is to use AI to evaluate the impact from cascading events, specifically looking at the impact of flood risk after a fire. So we have a project that we'd like to kind of see what we could do in a couple months on this topic. And then the second is kind of research and insights looking at some flood mapping data. So we've had that historic flood events data set, which is all the point features. And so we're looking to maybe try to explore that data set, looking at some temporal and statistical trends of flooding over the data to see if we can find hotspots and trends. And then the second part of that project would be looking at some flood hazard data and generate risk information. So we could use some flood hazard polygons that we have collected from the provinces and the territories, combine that with the record depth tool that I just described, and then have that flood depth information into another tool that we've developed called CanFlood that will allow us to kind of generate risk assessments. We wanted to see how that workflow might work. So those are kind of 2 potential projects for the summer. And with that, thank you very much for listening.
Thank you, Heather. Thank you very much for your thorough presentation. It was really nice to hear and learn about it. Do we have some questions for Heather in the audience? Est-ce qu'il y a du monde qui ont des questions? Je suis certain qu'il y a des gens qui ont des questions. Mais je peux commencer. So I will start. Oui, Saïd. Yes, Said.
Hi, Nicholas. How are you?
Hi, good.
Thank you for the presentation. I had just a small question about the training data. I saw you selected the 10,000 training data and from single site. So, what was your criteria for selection this training data? You just select it randomly, or for example, it should be near to the river, or did you have any criteria, or why you did select 10,000? And did you try to, for example, maybe the 5,000 or less than it, or what was your reason for selection that this number of data?
Yeah, thanks. Good question. We did try with a couple different distributions. We tried with I think 2,000, 5,000, and 10,000 that the student had looked at and found that the 10,000 gave us slightly better results when we ran the model. The criteria for selecting, so we had generated kind of this rough polygon of what our kind of study area extent was going to be. For the wet pixels or the flooded pixels, we just had them kind of randomly within the floodplain itself, within that polygon, but not in the permanent water. And then for the dry pixels, it was just anywhere randomly beyond the flood polygon to the extent of that rectangle that we had randomly created.
Oh, okay, thank you. So next question is about the because I'm actually working on the flood mapping now. So I'm clustering the SAR image. So in your experience, how did you find do you prefer to cluster or classify one single SAR image, or you prefer to the multiple patch and classify and apply your clustering or classification methods on that small patch? For example, maybe 512 per 512 every patch, or you prefer to apply a large image? What was your experience in this?
For these particular projects, we didn't use any SAR data at all.
Yes.
I have used some SAR data with another project that we looked at where we had more of a time series of data. And we were looking at more kind of the interferometry and kind of time series of the SAR data.
Mm-hmm.
For maybe to answer the second part of the question, for the sampling, we didn't really have clusters. We just dissolved the polygon into one feature and just randomly let it select with inside there.
Okay, so if our data is optical or it's not SAR imagine. So my question was about the patching the image or considering the whole image totally. So it can be SAR image or it can be optical image. So did you have some, for example, the results from the patch based or this all single? No. I just want to have your suggestion and view about this problem. So when you consider a large image for flooding, so you need to have a general, for example, thresholding. It is not this, so certainly locally, when you look at the image locally, so you can define the local threshold or general threshold. So this is one of the issue. I think it should be solved in the flood mapping. So how you find in this threshold? And because that's when I asked your question, I asked your opinion about that problem.
Yeah, and again, unfortunately, we didn't really use any optical or SAR at all. It was just kind of like climate and terrain data sets. So we didn't necessarily have to deal with like looking at the different bands of the imagery and figuring out thresholds in that kind of manner. So I can't really answer that, unfortunately, for you. But I'm going to be able to forward you to somebody who could.
Thank you.
Thanks, Said.
Thank you, Mr. Kala.
Do we have another question? Est-ce que quelqu'un d'autre veut poser une question à Heather? Oui, Ghazaleh?
Hi, thanks a lot for your thorough presentation. I just had a question about, you talked about flood risk and its relationship with fire. I just wonder that if the fire increases the risk of flood, or as we know, the fire, if we have a fire and then we have a flood, this will really decrease the situation and makes it really severe. Do you mean this one, or is there any relationship between a fire and the risk of the flood after that, or do you have any data about that?
Yeah, that's a great question. Thank you for asking. I haven't done any research or testing yet myself. I've read a few papers and I do know a bit of knowledge. So typically after a fire, the risk of flooding will typically increase, and that's in part because you don't have trees in place to kind of absorb some of the moisture that's coming down. It the reeds take out water. It will kind of cause some roughness, so the water might flow differently. And then you've got kind of this burned surface on the soil, so you don't have as much infiltration. So typically after a fire, there is an increased risk of flooding, from my understanding of what I read in the literature. But yeah, part of this project might be looking at that, to what impact or what percent or what magnitude, or maybe there's places where it doesn't increase the risk.
Thanks, Ella.
Hopefully that kind of answers your question.
Yeah, it was. Thank you.
Thank you, Ghazaleh. Do we have someone else with a question? if not yet, I would have one either, one or several, but I'll start with one. I was curious when you talked a bit about the kind of climate simulations that we did regarding like flooding extents. When you applied the RCP 2.6 scenario, I saw that for the year 2060, basically the probability of flooding and the flooding extent was like way less than the other years, like 2040 and 2080 and stuff. I was wondering if you had like any idea why it would be like less extent like 40 years from now than 20 years and 60 years.
Yeah, and that was actually a question that Aaron and I talked about, and it had to do with some of the kind of uncertainty in, I think it was in the precipitation values that as we're projecting get greater uncertainty and have less, we're less sure of. So we think that's the reason why the value hasn't changed that much, is because we see this greater uncertainty in some of those precipitation values in those long looking forecasts.
All right. And but in the meantime, when you look at like 2080, and 2100, like you have again like very large extent for the flooding. So it's just like for this range of 2060, it's a lesser extent.
Yeah, and there's really no way to like test or validate that in any way. But yeah, it is all quite large and quite high. So yeah, I think that's something that we could look at a little bit further to see if we could do some additional work on that to see if we can refine that in any way.
Yeah, it was very interesting to see like with different climate scenarios, like what it could be like in the future. I was wondering also, like, because you showed clearly that with the Gatineau and Ottawa region, like with the help of the more training data, like how it improved the results of your simulations. And clearly, apparently, you lack a lot of training data in many areas. Like, is there like any plan to like acquire more training data or to work on some training data to help improve all your models?
Well, we do have this flood hazard identification and mapping program where we are partnering with the provinces and territories to help support and get more of the high resolution flood hazard maps that we could use for training data. So that will certainly be a great source of additional training data that we can hopefully leverage in order to try to create those polygons of the 100-year floodplain. But other than that, yeah, I'm not sure how we might go about developing more training data other than using those engineering models and seeing how far we can kind of push the model outside of the region that it's been trained. Part of the problem with the single site in the Ottawa-Gatineau region was there's kind of some steepish kind of cliffs along the edge of the Ottawa River on the Ottawa side, and it just kind of didn't have enough variability. So once we added in those additional kind of east and west sections, it really gave us a little bit more diversity in the training set and was able to do better.
Oh, nice. Do we have someone else with a question? Because if not, I think we could wrap it up here. I would just remember that the internships that Heather talked about, you can find also like information about it on the DOTS website that from the DOTS program that I manage. So Heather like send us a few internship opportunities that we publish there. So you can find all the information over there. So, well, if we don't have any more questions, well, thank you very much, Heather, for your time and taking the time to answer the question and presenting the project and internships. It was very instructive and very appreciated.
Yeah, thank you very much for the opportunity. It was nice to meet you.
Thank you. Have a good day.
Thank you.